Homework was not short.
No, not as short as I said it would be. All right. Oh yeah, that. I guess so. That's right. Huh? Yeah, I guess I can't. I think there are fewer questions though, no?
There were 9. It's the same as homework.
Oh shoot! Yeah, you're right.
Except there were words.
Yeah, there is more stuff. There is more stuff questions.
Oh. All right. Well. False advertising. All right.
See that homework? There is a homework drop, right?
Oh, what now?
Homework drop.
Yeah.
I don't think it'll be this. Oh, it'll be this one. Well, yeah, you got what, 96, 92, 96. Yeah. So that's no, nothing's changed. We got tests after Thanksgiving, and then we have one review on Wednesday, and then Wednesday after that.
Yeah.
At 8 a.m. At 8 a.m.
Woohoo!
Yeah.
Oh,
I'm not even looking at 6 today.
Yeah, I gotta get on 6.
Yeah.
I gotta set like 6 extra alarms.
Yeah. So, yeah, homework 3 is due today. Those who have it.
Homework 6.
Or 6. Exam 3. Sorry. Exam 3 is what we're talking about today. 6 is due. Yeah. Thank you. Right. And right as the announcement I sent out, it said, right, we're not moving any dates after the exam from when they are in the syllabus. People that said they did not want to for different reasons. And so because of that, I'm just not going to move it. Like I said, when I've moved it before in the past, it's been either no objections or maybe like one soft objection or something like that. So I'm like, well, I kind of prefer this, but whatever, type of a thing. But there's more people this year. So, but yeah. So we'll again have a week from today, exam 3. And then a week from the following Wednesday from that will be the final at 8 a.m. Right? So, and that's, and so we'll review today, and then next week on Wednesday, we'll review for the final. And that's the semester. Fun stuff. So any questions kind of before we get going today on stuff? That's a good question. On the final, I haven't thought about it. Yeah, and most likely exam 3 is still going to be somewhere around 4. I haven't actually written exam 3 yet, so I don't know for sure, but somewhere around 4. Yeah. Yeah, for this class as well as exam 3 for my Gen Chem class. So fun stuff. Yeah, so, but for the final exam, right? So the question was how many questions are going to be on the final? I mean, my guess is it's not going to be too much because while we have what you get like 2.5 hours roughly for the time window, right? I'm not going to plan for it to take like at most I'll plan for the exam to be closer to like 2 hours, which is like 30 minutes more than our current exam. Oh, is that right? No, I guess 45 minutes more, right? We get an hour and 15 roughly. Yeah, 75 minutes, hour and 15. So I mean, my guess is it'll be closer to 6-ish questions on the final. Maybe if some of them or one of them has all parts or something, maybe 5 or something. But it's not going to be too many more questions. I think most likely it will be at most 2 more questions, like 6. Just as I don't want to make the final scheduled to take the entire time. Like if the final, I haven't figured out exactly how long you'll have for the final and things like that as well. But yeah, because typically what it was is you would just take the ACS final exam, which was I think 100 minutes for 50 questions, and that was it. So you had 100 minutes, took it and done, and there were multiple choice, and you had no calculator. Yeah, well, there were questions like, let's see here, something that's like, what is the work, right? I expand. Oh my gosh, sorry. That's all right. Well, I'll write this out. So let's see. Let's say we expand external. Right? Like you have something where you expand a gas, P externals, blah, 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 like work equals what, right? And the answer choices would be like 3 times 5 minus 2, negative 3 times 5 minus 2. And I don't know, whatever other things, I mean, they might just say like, they might expect you to do like 5 minus 2 is 3. So they might have like 9, negative 9 and whatever other things, right? So I don't, but if it was like, reversible isothermal and you had like nRT ln V final over V initial, right? They would have like numbers plugged into this without multiplying them out. That you would need to identify this is the right formula to plug into your calculator, right? And they would have other options like P delta V is probably would have been one of the options, and like some other kind of random formulas with the different numbers in the problem given plugged in different ways, and you'd have to like pick and identify, okay, this is the right equation and this is the right like set of numbers plugged in the right spots, type of thing, right? So that's how they do it without a calculator. So, but yeah, so we're gonna see how today goes. I don't know how the hell I slept, but I can't move my arms to save my life without excruciating pain. So, yeah, my daughter's going through a phase where she wakes up almost every night calling for my wife or I to go consult her. Their bed is not comfortable for me. So it's a real problem. But yeah, so that's also why for those who are in class, they're seeing me sit down right now. Is I'm seeing if this helps with, because like I can't look down. I can't look down. So I'm just lowering myself, getting myself closer to where I write, and I don't know. Yeah. Anyways, so other questions people have. Again, and I don't even know. I might even try to make the final just like an hour and a half, and maybe I'll just do 5 questions. I don't know. Like I don't know. Like yeah, and I definitely am not going to try to make the final like time to 2.5 hours or something. At most, I'll have it timed out to be close to 2 hours, and it might even be closer to like an hour and 45 minutes or something else like that. I just need to see kind of how many questions I feel like I need to put on there to kind of cover the bases for the course and how long it takes and blah, blah, blah. So again, I'll have a better idea of that. I'll probably also start trying to work over doing the final this Thanksgiving break as well. And so I might have a better idea of that come next week when we can review for it. So yeah, I will be around Thanksgiving break. I'm not going anywhere. And again, for those who are potentially traveling home to Thanksgiving break, and if they decide, you know what, I want to just stay home, let me know. That's fine. You can sign up to take the final and the third exam and things like that virtually. That's okay. I got no problem with it, especially if you're flying. So I guess if you're flying, you'd already bought your return tickets, then, you know, kind of too late. But yeah. Point being is I've had some people already contact me about this, and want to just again remind people that I'm more than happy for people to not come back if that's what they prefer. Okay. So, but yeah, but I will again. We'll be here. I'm not going anywhere. Not seeing anybody. You know, and whatnot. So. I'm going to stick around and be here in person next week. All right. So any questions before starting kind of reviewing for exam 3 here? And again, how we'll do this exam is all, again, just go over kind of the general ideas, concepts, and equations and things like that. And then I have different example problems worked up that we can do, but I'm also happy to work up different, like whatever examples or do whatever questions and whatever things people want from class and on Zoom here, okay? So, all right. So again, right, so this exam, we started off with kind of our 2 component phase diagrams and mixtures of 2 things, right? We got activities in this exam, chemical equilibrium, Boltzmann distribution, electrochemistry, right, are all the kind of things that we've talked about since exam 2. I think that covers it. I guess I can look at the syllabus real quick. Because yeah, colligative properties ended up being on exam 2, so not that yet. So activities, 2 component phase diagrams, equilibrium, electrochemistry, yep, and then Boltzmann statistics. So yeah. And then the next couple of slides, I'm going to have some equations from some of these different things. And just keep in mind that the red highlighted equations are things that you should know. And the white ones will be given to you. Okay. So I didn't break it up into like titled things. I broke it up into like sections in terms of, you know, the equations relevant to those topics. And then just use color coding to determine which ones you need to know, which ones you don't. Okay. So for mixtures of liquids, right, 2 component phase diagrams and things like that, there's, you know, a lot of these are things that were also relevant for exam 2, right? Things related with either total pressures, related with the mole fraction in the gas phase and partial pressures, right? Molar volume type things. And you don't really, I guess I could have scratched this one. This one you don't really need to know for this. So you're not going to have a molar volume question, but, you know, 2 component systems, right? The sum of the mole fractions in the liquid phase and the gas phase have to equal 1, right? Raoult's law, Henry's law, things like that, right? These equations you'd be potentially given for mixtures of two ideal gases or two ideal solutions or things like that in terms of total pressures and vapor pressures of pure solutions and mole fractions in gas phase and liquid phase and blah, 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 right? But again, red you should know, white would be given if you need to use it. Again, even within the red, some of this partial molar volume stuff, I guess I didn't really need to input there because we're not going to have a partial molar volume question on exam 3. Okay. Any questions about these equations? Any that people thought I left off? I guess you could put the, I guess did I have it? No. I guess one that's not here is the phase rule, right? The number of degrees of freedom equals the number of components minus the number of phases in equilibrium plus 2, right? That phase rule. Okay. I guess I could type that up, add it real quick. Just, why can't I see the river? My fingers are off. Again, looking down is not fun. I'm doing this stuff. Looking here is fun. So yeah. Get rid of that equation. Okay. Right. That phase rule. These slides are on Canvas. I forgot to post them earlier, so I just posted them this morning, right before class, but they are on Canvas. And I believe that the equation should still be color-coded on the ones on Canvas. I'll double check that, but I think they are. Question? No, not right now? Maybe I didn't publish them. Oh, you know what? I think. Let's see here. I maybe having permissions wrong or something. Let's see here. 30. Maybe I accidentally put them on the wrong class here. Get the files. No, lecture slides. Okay. So, yeah, so it should be posted. You should hopefully be able to see it. I don't have it linked. Did I make a module thing for exam 2? Did I post that anywhere? Maybe I'll just send like a, no. All right, so I'll also make an announcement where that's linked to it, or maybe I'll just link it on the homepage. That's what I think that's what I did last time. Yeah, there we go. So let me do that right now. But yeah, so yeah, I just posted this right before class, so that was kind of on me. Forgetting to do that earlier. So, but yeah. Okay, right, for activities, right, just kind of your definition of the activity, okay? Right, for solvent, for solute, right, and for salt, okay? Right. I guess you'll notice here that I'm just not going to. Yeah, I mean, fugacity is not up here. Don't worry about fugacity. Right. That's fine. I was debating of whether or not I want to ask a question on it, and I'm just making the executive decision. No fugacity. Don't worry about it. Right. But yeah, but so here's, again, activity for your solvent is related with mole fractions. Activity for the solute, right, is related with its molality. B here's molality. Activity for salt is again related to molality, but the main thing is the activity coefficient. The is the mean activity coefficient from the bi-Huckel equation. Okay, log of gamma plus or minus equals this. You don't need to remember what A is. Okay, you don't have to memorize A. You'll be given the value for A. It's roughly 0.509. Yeah. Yeah. So, okay. And you don't have to memorize the bi-Huckel equation, but you do need to remember what the ionic strength is. Okay. And again, a lot of equations that you do need to know versus don't need to know were based off of the ACS final exam and what equations you were given there. In there, you were given the bi-Huckel equation, but again, you weren't given the equation for the ionic strength. Yeah, question?
It was about the homework.
Yeah.
On question 8, where we were using the bi-Huckel like limiting law and activities, there was like, if you were told that there's a certain molar solution at the cathode and another molar solution at the anode.
Yeah.
Does that mean that there will be 2 separate ionic strengths that will need to calculate?
Yep.
Yes. I just want to make sure.
Yeah. Yeah. So that electrochemistry example on the homework, which I'm happy if we want to go over that or a question like that, right, is, a good question because it combines a lot of things, right, in terms of activities and mean activity coefficients as well as electrochemistry, right? And the main thing to keep in mind, right, for that problem is that you have separate solutions for the anode and cathode, which means each solution has its own ionic strength, right? We talked about before when we talked about these mean activity coefficients, right, that for a solution, the ionic strength is a solution property. No matter how many different salts you have in there, right, there's one ionic strength for that solution. But for something like electrochemistry, where you have solutions that are separated, right, then you do have 2 separate solutions, so they each have their own ionic strength, right? That depends on how much ions are dissolved in that solution. So, yeah.
Could we
All right.
go over a problem similar to 8?
Yeah. So we can go over a problem similar to the one on the homework. We'll do that. We'll do that first after we finish the equations, which this is, I think, the last slide on the equation, right? Yeah. Right. And then there's equilibrium electrochemistry. And I guess I can throw in the Boltzmann distribution. I'll do that real quick. Oh, no, wrong slide. And so this also kind of includes Boltzmann distribution, right? Oh, should that be white or red? Let me decide. Nah. Next semester you might have to memorize it, but this semester that's fine. I'll give them to you. But you need to know how to use it. But yeah. So those equations again in red are ones you need to know. Why do I have that? I don't know. Yeah, that's weird. Again, what's given in not is based off of the ACS final, and I guess at ACS final they give you the Nernst equation with plugging things in, assuming 25 degrees Celsius, but they don't give you it without plugging things in at 25 degrees Celsius. So that's wonderful.
The Nernst can only use at 25 Celsius, right?
Well, this one.
Right.
This is any temperature. The actual Nernst equation is at any temperature, but this 0.0592 is at specifically 25 degrees Celsius, right? Okay. Okay. The Van Hoff equation is something you'd be given, while the integrated form of that Van Hoff equation, which is here, right, is something you need to remember. Okay. And again, the relationship between delta G and K, and kind of the free energy version of the Nernst equation, you also need to know.
So anytime we would use the regular vent off and not the.
I mean, if you had a plot and you wanted to look at the slope of the plot or something, I don't know. Not necessarily, but again, I'm just all equations in white, except for I guess those last two, again, are equations that are given for the ACS final. And so I just,
I got it. I give it to you and you can
Yeah.
grade it yourself if you don't remember the.
yeah. So that's, again, the ACS final, they give certain equations and they give what they give. And I just try to stay consistent with that throughout the semester. Even though this year we're not doing the ACS final, I just kind of keep things consistent. I'm doing that. So, any questions about these equations? Anything? All right. So, all right. I guess I have Canvas open. So I'm not going to do question 8 exactly here because, well, people watching on Zoom technically could have not turned in their homework yet. Or I guess people working in class could also be doing the homework or something like that, right? So I'm not going to do question 6 here, question 8, but I'll make up some question like 8. All right, so let's see here. Standard cell potential. Did I go over to line notation? Yeah, okay. Then I'm just going to write out the equation in line notation here. I'm just going to make up something. Cu2 plus. I'm just going to make up a cell potential or something here. All right, download. All right. And then the thing is we got then concentration of Cu, L2. All right. Okay. So here we go. So this is the problem. Right. We have that electrochemical reaction. Okay. That has the standard cell potential that I made up completely at 0.59 volts or negative 0.59 volts. And I have, for this system, right, I have a solution of CuCl2 on one side, zinc SO4 on the other side. Oh, you know what? Let's see here. So anode, cathode, I'm just gonna put there. And in this solution, the side with CuCl2 I add 0.85 molar NaCl. All right. I have to add a cation to this to actually have cations that flow to the other side of the solution, right? So, I mean, question 8 doesn't have that or something like that, but here I'm deciding if I were to actually make an electrochemical reaction like this, right? I'd want to make sure that in my anode side, I have cations that can flow into the cathode, right? And currently, right, if I were to have any cation flow into cathode, it would be Cu2 plus, which would then just short out my electrochemical cell, right? It would bypass the electrodes and things like that, right? Because then I just have the ions flowing to the other side and undergoing the electrochemical reaction within solution instead of making the electrons transfer through my electrodes, right? And so I need to have some sort of cation in solution that's not involved in the reaction. And so I'm adding sodium chloride to the copper chloride solution. Huh? So again, yeah, I'm not trying to do exactly question 8, but something very similar. So, so I'll take a second, at least, go through and write out how you'd work this out for ideal, right? I'm going to say this is at 25 degrees Celsius. I'll just give, right, E cell, E cell not, minus 0.5, 0.0592 basically, N log, right? I think I remember that correctly. Huh? Oh, sorry, yeah, and sorry, in my Gen Chem class, the book has N as the number of electrons transferred. In this class, in the textbook here, it has V. So yeah, sorry, that's why I put N. But yeah, V, right, is that stoichiometric coefficient number of electrons being transferred. Here, do that there. Oh well. Oh well. Whatever. All right. So if we were to do first the ideal case, I here, right? For the ideal, we just use this equation and plug things in, right? E cell equals minus 0.59 volts minus 0.0592 divided by 2, right? In this reaction, right, I guess we kind of write it out, right, that the electrochemical reaction involved, right, is Zn2 plus plus Cu going to Cu2 plus Zn, right? That's my electrochemical reaction, okay? Right, and so the log of Q is going to be just the log of the concentration of Cu2 plus divided by concentration of Zn2 plus, right? Did I just do that in the exact opposite way? Yes, I did. Fantastic. So we plus that. Yeah, whatever. And so, right, you just got to plug in the 0.48 and 0.92, right? So I get 0.92 is concentration of Zn2 plus, or 0.29, sorry, 0.29, right? So just plug in for here 0.29, and then for this, plug in the 0.48, okay? And you'll get the E cell equals minus 0.596 volts, I think. Yeah, right. So that is the cell potential under standard condition, or not under standard conditions, right? Assuming ideal behavior. So any questions about this first part? All right, for the second part, okay, we need to do the same thing, same equation, everything, just the concentration of our ions isn't 0.48, 0.29, but it's these guys times the mean activity coefficients in those solutions, right? And so we got to calculate what is the mean activity coefficient for the anode and the cathode, right? So gamma plus or minus for the anode, right? This is a solution, right? At the anode, I have Cu2 plus, plus 2Cl minus ions, right, being introduced. And then I also have the Na plus the Cl minus ions being introduced, right? But concentration of these is 0.48, 0.96, 0.85, and 0.85. Okay. Right, the concentrations of ions at the anode. Any questions about that so far? And so my ionic strength is going to be 1/2. Now the charge of copper is 2, so it's 2 squared times 0.48. The charge of chlorine is 1, so it's just 1 times 0.96. Charge of sodium here is 1, so it's 0.85, plus again another 0.85. Okay, so you have 1/2. Here I can kind of manual zoom this stuff here. Right, so we got 1/2 times the sum of 4 times 0.48 plus 0.96 plus 0.85 plus 0.85, right? Anyone have what that comes out to be? Huh? Sorry. 2.29 is the ionic strength of the anode, right? And so the mean activity coefficient, the anode, right, is it's just exponential, right? Exponential of minus, right? Specifically for copper, right? Cu2 plus, right, is going to be 2 times 1, right? Times 0.509, which is A, times the square root of 2.29, right? Oh, you're right. This is 10 to the, yeah. I was trying to remember the equation off the top of my head for that debacle. Yeah, you're right. It's log gamma plus or minus equals minus. Yep. So yeah, it's 10 to those things. Okay. So that's The charges are 2 and 1. I put the absolute value here. This is like the absolute value, right, of the charges 2 and 1, right? Because I'm looking at the anode specifically for CuCl2, right? This is the gamma plus or minus for CuCl2 at the anode, okay? And so the charge of copper is 2, charge of chlorine is 1. Oh, yeah. So I just didn't bother writing the ones out, the 1 squared. Oh, yeah, that's a 4. Yes, that's a 4. Yeah. This should be an 8, right? This is an 8. Yeah. You can all admire my penmanship. Right. 2.29. Square root of that times 0.509. That times 2 minus, where's 10 to that? All right, so I got, and someone can tell me if they got the same thing. I got gamma plus or minus for CuCl2 is equal to 0.0288. I don't know if anyone else calculated things got the same number or a different number. Question?
So for the mean activity coefficient, is it specific for every like cation and anion pair, or is it just for all these species, like in that solution that you calculated? Or like say I added like something like ferric nitrate and just now I have 3+ iron in there. Would I have like in that absolute value, do I now have 2, 1, and the 3, or do I do it specifically for the ferric nitrate pair?
Yeah, so the mean, so the question is, right, basically, is the mean activity coefficient for all ions in solution or unique to a cation-anion pair? And the answer is it's unique to cation-anion pair. The ionic strength is for the entire solution. It's not unique to any specific ion, right? The ionic strength is unique to a solution. But the mean activity coefficient is the average activity coefficient for the cation-anion pair of a specific like salt, right? So copper chloride here, right? I could calculate the mean activity coefficient for sodium chloride, right? Which would be different from the mean activity coefficient for copper chloride, right? And if you had the ferrous nitrate or something like that, as you're giving an example of, right, that would have its own mean activity coefficient from the other guys. Yeah, so you calculate a mean activity coefficient for every pair that you have. I mean, for what you're interested in, right? I'm not going to calculate the mean activity coefficient for the added sodium chloride because I don't really care what the effective concentrations of sodium chloride are in the solution. I just care about the effective concentration of copper. So, yeah. Yeah. All right. Okay. So that's the mean activity coefficient for copper chloride. So I need to do this exact same thing for the anode, right? Anode's a little bit simpler. Huh? Oh, sorry, cathode. Thank you. Yes, I need to do the same thing for the cathode, right? I need to find that gamma plus or minus, okay? But the first thing I need to do is the ionic strength at the cathode, right? In this case, it's just 1/2 times, what's the chart? We got, what is it? Zinc sulfate, right? Going back up, I have zinc SO4 is the only thing at my cathode, right? So it's charge of 2, so 4 times the concentration of 0.29 plus 4 times concentration of 0.29, okay? Which gives me 2 times 0.29, right? So the ionic strength at the cathode is just 0.58, okay? And so then the mean activity coefficient of that zinc sulfate, right, is then 10 to the minus 2 times 2 times 0.509 times the square root of 0.58. Huh? Oh, you're right. It's 4 times that. Shoot. I was taking 4 and dividing it by 2, and it's like, oh, it's 2 times it. But then I have 2 of them added together. So it should be, yeah, thank you. So it's 1.16, right? 1.16. Thank you. Right. Yeah. So again, yeah, it's, I have 2 of these. So those 2 of those cancels out with the half. So it's just 4 times 0.29, which is 1.16. So do the square root of that times 0.509 times 4 minus 2 to that. So I got the mean activity coefficient for zinc sulfate is 0.006. Right. Okay. That okay. Right. So finally, right, to calculate the cell potential, right, which is what we're looking at, is at 0.59 volts, the standard cell potential, minus 0.0592 divided by 2 times the log of the concentration of Cu2 plus, which is at 0.48 times its mean activity coefficient, which is 0.0288, divided by the 0.29 concentration of zinc times 0.0064. Okay. And so that is my new reaction quotient, right? Using my activities. Log of that times that. And you get that E cell equal to, and if I did things correctly, minus 0.56, we'll say 4. Oh, sorry. Right. So if I plugged in these things correctly here and whatnot in my calculator, then I got minus 0.564 volts for the cell potential of the system. I fix the paper. Sorry, Ricardo, I just saw your comment. Did I fix the paper? Did I do what you're asking? Oh, yeah, okay, fantastic, okay. Sorry about that. I didn't see the comment earlier. So yeah, right. So, and if we compare with above, right, not a big difference, but, you know, a couple tenths of a, or hundredths of a volt, right, minus 0.596 versus minus 0.564 volts, right, using ideal and non-ideal, right? Now, obviously, there could be a bigger discrepancy if I pick different concentrations for my ions and things like that, right? But that's fine. Right. Or if I had, yeah. But anyways, so questions about this? problem, this is an example problem, how to do it, why we did what we did. Yeah.
I just have a question regarding going to number 8 specifically for the concentration. So whenever you do the first part, you go up for the ideal.
Okay. So are you actually wanting to look at number 8 or?
So my question is just with the molarities of the solution. Whenever you did the example problem, you did concentration of Cu2 plus over Zn2 plus. Well, both of those are Sn only on one side of the reaction. So then we just do molarity of anode over molarity of cathode for our Q.
Oh, I see. So what? Okay, so at anode you have SnCl2.
I just assumed you meant copper chloride instead of tin.
Oh yeah, I put tin for both of those. Huh. Oh yeah, no, it should be, yeah, it shouldn't be tin for both of them because then where's the copper?
Yeah, we just assumed it was just
Cop.
solution over solution.
Yeah, yeah, this should be copper chloride at the anode, right? The anode has the oxide. No, oh sorry. So this should be copper, copper phosphate. This should be the copper because at the cathode you have the copper. So this should have been copper here, not tin. All right, I will have to keep that in mind when grading these things to see kind of what people did. Since, yeah. Yeah, yeah. The thing is yeah, if you didn't, I mean, I don't know what one would have put in for the concentration of copper in the reaction quotient without assuming one of these things had to be copper, right? But yeah, that was just a typo in which it should have been copper. Now, if I added, right, I mean, so going back to kind of thing, right? So let's go back to. Oh, I'm still sharing this. Sorry, people online didn't. Yeah, I was looking at the question 8 from the homework, right? But if I go back to this, right, one of the things I could kind of ask about is, well, what is the activity of chlorine in this solution that contains chlorine from copper chloride and chlorine from sodium chloride, right? And to get the activity of chlorine, right, what you'd have to do is calculate essentially what is the activity, right, the effective concentration of chlorine from this salt and add it to the effective concentration from this salt, okay? Right, because there isn't a mean activity coefficient for just chloride. There's a mean activity coefficient for chloride in copper chloride and a mean activity coefficient for chloride in sodium chloride. So, right, the concentration, right, in this solution, right, the concentration of chloride, right, or I should say the activity of chloride would actually be say that 0.96 times the activity coefficient of copper chloride plus 0.85 times the mean activity coefficient of sodium chloride. Okay. So the activity would effectively be the activity of chloride in copper chloride plus the activity of chloride in sodium chloride, right? Just sort of like, right, the total concentration we think of is the sum of the concentration of chloride from copper chloride and the sum of concentration of chloride from sodium chloride, right? You do the same thing, it's just you can't add up the concentrations and then multiply by the mean activity coefficients, because again, the mean activity coefficients aren't necessarily the same for the two ion pairs, right? And in this case, they aren't. Gamma plus or minus for sodium chloride and gamma plus or minus for copper chloride are not the same gamma plus or minuses, right? And so in the, if you're to try to, if you assumed in the homework problem that both compounds were tin compounds, right, then it would be more, you had to get the total tin concentration, right, and calculate that. But again, then I don't know what you'd have used for copper when plugging in for Q if you just assumed 1 or whatever. But I'll keep that in mind and look at that when I'm grading question 8, since there's that typo there. in which I put tin for both compounds, even though for the cathode, where the reduction occurs, it should have been copper. Questions? All right, other example problems, example questions people would like to see?
Did you try and make up one similar to question 2?
See what question 2 is on the homework here. Molecular bromide is 44% associated, and 1 bar. Go to math, calculate equivalent constant at that temperature. And then part 2, calculate it at that temperature given delta H.
I guess just the,
Mhm.
oh, okay, so I calculated, for part 1, I thought it was Celsius, so I thought you meant to do it, a second one for the 6.
Ah, crap, yeah.
But yeah, I guess it's just figuring out the first case value. It's the
Okay.
second one is the part.
Yeah. Yeah, so I'll have to look at my answers to see if I assumed.
1600 Kelvin and 1600 Celsius.
Yeah, exactly, right.
Yeah.
All right, so I'll look at my solutions. My gosh, this homework. Right, so the issue I'm kind of seeing here is that this is at 1600 Kelvin. I'm going to guess I meant for this to be 1600 Kelvin and that to be 2000 Kelvin, but I obviously put Celsius. So if you did the problem with Celsius, that's fine, and I will make sure that my answers are consistent with whether or not you used Kelvin or Celsius. So I'll look into that. There should be a very large difference because, right, you add 200, well, it'll be some difference. So, but yeah, I'll answer the question as written, okay? So the main thing is, right, let's assume, grab a blank piece. Grab a blank piece of paper here. All right, so, L2 going to 2Cl. Is 28%. At 1500 Kelvin. All right. All right. So, right, I am looking at dissociation chlorine at 1500 Kelvin. Question is, what is the equilibrium constant, right? And so for this, right, I know it's 28% dissociated, right? Which means, right, that, and again, right, so we're going to assume some initial concentration, and I can do that because, right, the equilibrium constant, right, should be independent of that assumed value, right? I didn't give you a specific value, right? Just making sure. Yeah. Okay. Right. So in this case, right, if we assume we have 1 bar, if you will, of this, okay, right, start off with 0 of that, right? To reach equilibrium, 28% of that is associated, which means that I'm left with 72% or 0.72 bar at equilibrium. Okay, so my initial value is 1 bar, equilibrium value of 0.72 bars, so equilibrium value of chlorine here is going to be 2 times 0.28, so 0.56 bar. Okay. So this is the equilibrium pressure. So I get that because, again, I have 1 bar, 28% dissociation means I lose 28% of 1, which leaves me left with 0.72. And then if I've lost 0.28 of Cl2, that means I gained twice the amount of Cl, so that's 0.56 bar. So right, then K is just going to equal 0.56 squared over 0.72. And I think that will not matter. Let's see, if I said did one instead of 1, I did X, I would have X. This is basically what's left is 72% of that, so X times 0.72. And then this is 2 times 0. So actually, I wonder if I times X. Right? Equilibrium concentrations. I'm trying to think if it should matter what you assumed the initial value was.
The only reason I was wondering is because in the problem it said it had an equilibrium pressure of 1 bar. So if those were ideal,
Oh,
assuming ideal.
In that 1 bar. Yeah, so the total pressure, okay, so only 40% association and 1 bar. Aha, yeah. So it is the total pressure of 1 bar. Okay. Yeah.
If I'm honest, I had to look at the book for how to solve it, and they did it in a way that we hadn't covered directly. So this might be some kind of.
Yeah, no. So the no, thank you for pointing that out. Yeah. So the pressure is P total is equal to 1 bar. So I didn't realize that. So the initial pressure is not 1 bar. It's the total pressure at equilibrium, right? This is at equilibrium. That pressure, total pressure is 1 bar, right? Which, right? Which which at P total, right, is the equilibrium value of Cl2 plus the equilibrium pressure of Cl. Okay. Which again, we know that is 1 bar. Okay. And then basically, if I wanted to figure out, I guess what I was doing actually would help me figure that out. Right. So the equilibrium pressure of Cl2 should be whatever the initial pressure of Cl2 is, right? Initially, I would have started off with just Cl2. So some initial pressure, X equals P initial of Cl2, okay? Right? And the equilibrium value is going to be 0.72 times that initial pressure, right? Because I've lost, right? I lost 28%, right? So if I've lost 28%, 72% is left. So what's left is 0.72 times that initial pressure. And then the final equilibrium pressure of Cl2 is the 28% that was dissociated times 2 because of my stoichiometric coefficient. So it's 2 times 0.28 times X. Okay. And so that would give me actually what the initial pressure is, right? So that gives me what X is by solving this equation. What? 2.8 times 2 plus 0.72 and 1 divided by 1.28. So X, which is my initial pressure, Cl2, equals 0.78, 1 bar, which means my equilibrium pressure, Cl2, is going to be 0.72 of that, which is 0.563 bar. And then my equilibrium pressure of Cl is 0.781 times 0.28 times 2, 0.437 bar, right? Which these two things added up will give me a total 1 bar pressure, okay? And so then K is equal to 0.437 squared over 0.563. Right. So 0.34, basically. Yeah. And so, right, what I was getting at when I was doing this, I was trying to see, should my final answer depend on the initial pressure? And I was looking at this and I was seeing that it does. That it does depend on the initial pressure of your final answer. And so, right, the other key piece of information in that problem on homework 2, or on the homework 6, problem number 2, was right, is it telling you that the pressure is 1 bar. So that is telling you what the total pressure is for this equilibrium reaction, okay? So hopefully, if you were to do this exact same thing, but instead of doing 28% dissociation, you did 44% dissociation, you get the same answer. Or you get the answer that's there. But I don't know what the book exactly did, if it did something kind of like this or what.
It seems pretty similar. They just they broke it down kind of in like, yeah, it's a similar way that you did it.
Okay.
I can start to explain the words. I just had to look at how they did it.
Okay. Yeah. So, so yeah, the main thing was seeing that the equilibrium pressures are these guys here, okay, where X is that initial pressure. Okay. But yeah. And then after this, right, once you find K, right, then it's just using that equation ln of K final over K initial, right, is related with minus delta H over R times 1 over T final minus 1 over T initial, right? Just kind of that expression to get the K at different temperatures, right? And you're given delta H and such. So other questions about this problem? All right, any other example questions people are curious about? From the homework? All right. You don't want to do any more homework problems because you'll find out you did them wrong. Yeah, I mean, on that one problem, on question 8, right? I'm going to grade that with some leniency if you use tin instead of copper for one of those ions, since tin was what was written, and things like that. So again, I'll have some fun grading these to correct for some of my typos. And again, for question 2 there, I'll also be keeping in mind, right, if you did Celsius versus Kelvin, or just assumed I meant Kelvin. But yeah. All right. So, you know, some of the questions, example questions, I'll kind of just go over the examples I have here. You can work on them yourselves. Solutions are posted, some more detailed than others, right? But I have here where I'm mixing some non-ideal things, non-ideal volatile liquids, right? And I'm looking for activities for these liquids. And then based off of these activities, what that Gibbs free energy of mixture is, okay? Right, so the main thing to find activities right, is given kind of the moles of these guys of A and B, and then the total vapor pressure of the solution, right? And then the mole fraction in the vapor phase and the vapor pressures of the pure liquids, right, will allow you to calculate what the mole fractions are in the liquid phases and things like that, right? And then once we have the mole fractions in the liquid phases, I can get this Gibbs free energy of the mixture, okay? Right, right, that Gibbs free energy of the mixture, again, is related with these mole fractions in the liquid phases and sort of those activities, okay, in those liquid phases. Okay. Right. When we talked about mixtures of ideal solutions, we had some expression like this, but instead of activity here, right, it was the mole fraction of A and the mole fraction of B, right? Well, for a non-ideal solution, it's activities, not the mole fractions. Okay. Right. But yeah. Here, just kind of an equilibrium problem where I'm calculating reaction quotient for something, okay, which is just going to be using the Debye-Huckel equation, right? So what this problem is all about, right? Finding your ionic strength and such. Okay, we have an ideal solution, volatile liquids, PA star, PB star, right? As the pressure is reduced from 450 torr, the first vapor is observed at a pressure of 70 torr. Calculate the mole fraction of A, right? So this problem, right, is basically telling you, right, that the vapor pressure of the solution is 70 torr, okay? Right, because, so in this problem, right, what you're doing is, right, you have, think of like your pressure versus total composition of A, right? You have, let's see here, I think positive slope and kind of like this, right? You have something where you're at some high pressure up here, right? And you're lowering the pressure till you reach this point, right? At this point, right, this is, right, this is this like, this is your like vapor pressure line, right? This is the line, right? This is the plot of sort of the vapor pressure as mole fraction, right? This is your vapor pressure, you know, as a function of the mole fraction in the liquid phase, right? That's where that plot came from, right? And so this being at 70 torr, right? Right, and at this point is when you first start getting some vapor occurring, right? All above this is liquid. In this phase, that's gamma and L, right? Liquid, right? In this phase, you have liquid plus a vapor plus your gas, and then in here you have the gas phase, right? So the first point in which you start getting gas phase molecules, right, is when that vapor pressure, right, is equal to the external pressure, okay? So when I start observing significant moles in the gas phase, okay? And so it's telling you that the vapor pressure basically is 70 torr in that problem, right? So this problem is, you know, a different way of basically saying in the mixture, you have 70 torr, okay, right? What is the mole fraction in the liquid phase, right? And so it's just kind of using this expression here. Well, this was to find the mole fraction in the vapor phase, but you don't really need that. Find the mole fraction in the liquid phase, but I guess you could. Could have used, right, for that calculation, you could have used this expression. Oh, I guess I don't have an expression given here. There should be an expression of P total in terms of XA, but not given here. But you should be, right, if you were to plug in YA here in terms of XA and simplify, you should get P total in terms of XA, and you'd be able to just use that expression to solve for XA. Okay? right? This is another equilibrium problem, okay? Kind of related with how acidic soda is based off the amount of carbon dioxide that's in that soda, right? Assuming that's the only thing contributing to its acidity, okay? It's just kind of an ice type problem, solving some stuff, okay? Another equilibrium problem, but here we're relating with delta G and the equilibrium constant. Here, just calculating some cell potentials, right? Again, just pointing up some phase diagrams to remind yourselves that you need to be able to understand what is going on in these phase diagrams for two-component systems. Right, and then here's just an electrochemistry example, right? Not detailed answers, but answers are at least given for these ones, okay? But yeah, if you, while you're reviewing this stuff, if you have questions about any of these examples or anything else, always feel free to email me. I'm happy to try to set up sometime to Zoom to chat as you're reviewing. Okay. But again, the exam is going to be a week from today. Yeah.
Your K value there is the solubility product.
Yeah, it's a KSP. Yeah. I guess I didn't put specifically SP that, but yeah, it's for solubility product reaction.
Are they always usually that small?
KSPs? Yeah. They're usually pretty small. Yeah, and I'll upload today's video as well. So I'll upload that and upload solutions to the homework today and whatnot. And again, if you have any questions, feel free to email me at any time. You can also schedule a Zoom meeting. So, but yeah, any other questions from those here on Zoom before I close the session for today? All right. So I'm going to end the session. I'll see you guys in a week. Have a great Thanksgiving break.